Perfect, thank you. All right, so today, what are we doing? Today we're going to continue talking about the structure of our galaxy, um, and then we'll talk about measuring the velocity of the galaxy that we're in, which is a headache. Velocity of galaxies that we're not in is actually a lot easier to do because we can see them. This one we're in, it's hard to see. It's kind of like watching a movie with your nose literally touching the screen of the TV. You can follow it, but it's really hard to see what's going on. Let's see. So I think actually I'm gonna get through everything that I wanted to today. So I think that I'm on track, and the reading was the right time. So it was a reading last night. We'll talk about more structure. Oh, the other thing I'm going to talk about. Talk about ore constants and all that crap. Okay, so I'm going to go through the questions one by one, just so I cover everything. One of you had asked the question, so I hope that I'm answering the right question. One of you asked, what's the deal with these parentheses without a ratio thing, without the line in the middle? That's a vector. So, and I'll go through this in detail, but he has, I think that the question was about, he has these things that say sine theta, cosine theta. This is just a two-element vector. So this is the x and this is y, or whatever. I'll go through that in medium detail. I'm not going to go through it in horribly painful detail because that's not useful for anybody. For you to watch me do a page full of algebra. It's useful for you to do a page full of algebra, and it's useful for me to do a page full of algebra, but it's not useful for you to watch me do a page full of algebra. So I'll point you to how everything works and answer the questions, and then if you care, you can sort out what these things are. What are A and B? A and B are the Oort constants, and what the Oort constants do is they let us take a measurement that's very difficult to make and turn it into a measurement that's easy to make, if that makes sense. Yeah.
Do the Oort constants only apply to measuring velocity in our own Milky Way?
More than that, they only apply to our own Milky Way for the stars that are pretty close to us in the galaxy.
Okay, because the name, I was like, that sounds like it's because of our solar system. I don't know why.
Yeah. It only matters for us. Oort was an astronomer in the 30s and 40s and 50s and early part of the century. I don't remember when he died. But his name's on a bunch of stuff, and he happened to be one of the people to sort this out. He also sorted out that there's a big cloud of stuff. There's a thing called the Oort cloud, which is surrounding the solar system. Oort did a lot of stuff. Why must there be dark matter? That could be the title of this class. I'm going to highlight this one, actually, make it bold. So, something's wrong, and I'll show you why. We need an answer. Might be the math, might be we're missing some stuff. It's probably not the math, so we're probably missing some stuff. That's the short answer, but I'll go through that in detail throughout the rest of the course. Basically, there's like 5 measurements that I'm going to talk about that all say, hey, there's a bunch of crap missing, or your math is all wrong. One of the two, you can sort it out. The math for each one is way different, but the net result is the same amount of missing material. So in several different ways, we'll talk about it, several different ways we measure how much mass is there by looking at the photons, and sometimes we measure it by measuring the forces, and when we don't get the same answer, then there's something missing. Yeah.
Is there a way to identify how long the dark matter has been around? If it's just been around as long as normal matter has been around, or if it like appeared soon?
One of the measurements is the light from the early universe. So the light from the Big Bang are the oldest photons that we can measure, and we see it there. We see the same amount there as we do when we measure galaxy clusters locally in the local universe. So it's been around the whole time. That's a really good question. So the light from the Big Bang shows us that there's dark matter. The rotation curves of galaxies show us that there's dark matter. That's the one that we'll talk about first because it's the easiest one to get your hand around. The statistics of how galaxies cluster also shows us there's dark matter. So we can say, hey, they cluster like this. They have this kind of statistical distribution. There has to be dark matter because the luminous matter doesn't get it. So do any of you watch Great British Baking Show? No. Have you ever watched a British person bake anything? The reason I bring up the British one is one thing that I didn't really understand when I was first watching the show a couple of years ago. When they're measuring out the flour, they just kind of dump it into the bin. They don't like measure with a measuring cup. I always measure with a measuring cup, but they use a scale, which now I learned is vastly superior if you're baking stuff, is to measure your flour by weight rather than volume. And that's really what we're doing with a lot of these measurements. We have two different ways of measuring the mass in the galaxy. We can either use the photons, which give us one answer, but that's just counting the stuff. Or we can use, that's like using a measuring cup, you just count stuff. Or we can use the forces on those things and say how much stuff must there be there. And they give us a different answer. So either our force calculation is vastly wrong, GR is pretty right, or we're missing some stuff, which kind of happens all the time. So a lot of science really comes down on, well, the answer is probably a missing particle. But we'll talk more in detail about those. Section 2.4.3 is about the gravitational potential, and a couple of you were a little confused about what he's talking about there. What I can see is this little galaxy. What I can tell is that that's not the whole thing. The whole thing is this big sphere of something that I don't understand. So for now, we're going to run with the assumption that dark matter is a particle that we haven't found, because that works pretty well. All of the math things are all super finely tuned and all really fussy, and none of them work. That's not true. MOND works really well for galaxies because it was designed for galaxies. It doesn't do crap for any of the other measurements. So some things work really well for the thing that they are designed for. Maybe there's more than one solution. Maybe we actually have 4 problems. That's entirely possible too. So okay, the galaxy. So we've got this galaxy. When I look at the galaxy by itself, and I say, I'm looking edge on, right? So it's rotating this way. This part is moving faster. Here's the center. This part is moving faster than it should. And this part, where there's nothing out here, is moving way faster than it should. So you remember, v squared equals gm over r. So the velocity and the mass are tightly related. So if I measure stuff out here, where there's not really any stars, there's some stars, and I can see that they're spinning around like crazy, but there's not a lot of stars, so there's not a lot of mass, so they shouldn't be really spinning around that crazy, but they are. Now, if we keep going out further, this is what that section is about, and this little short little section that's just like, yeah, we don't actually understand it. So I know that there's stuff out here, but I don't know if it's shaped like that, or if it's shaped like that, or God forbid it's shaped like that, but everybody would hate that. But since we don't actually know, we can't say. There's some weird things out there. All of the galaxies that are, so the Milky Way has all these galaxies that are orbiting it, right? Now, if you have a bunch of objects that are randomly orbiting something else, they'll be on random trajectories. The stars in the galaxy are all on random trajectories, but the galaxies are all on this plane that lines up like that for some reason. The satellite galaxies. So we don't know. So the galaxy lives in a big ball of dark matter. And that's what the galactic potential is. Now, maybe it's not dark matter, maybe it's just extra gravitational potential, but we have all of this extra gravitational potential. It's probably round, but it's not clear how round, is really all that section's saying. Yeah.
Is dark matter essential for the formation of galaxies?
Yeah. Otherwise, nothing forms. Otherwise, it stays low density the whole time. So without dark matter, we wouldn't be here. Okay, what causes stars to migrate in or out or up or down? So this is a good question with several answers. My grad student is writing a paper on this. I didn't have anything to do with it. He wrote it before he got here. But he's writing a paper on how stars move in galaxies. So the answer really is, and I just learned this on Tuesday from him. I have a galaxy and it's got these spiral arms. And it's got a bar usually in the middle. Well, sometimes there's a bar in the middle. If my galaxy is a sphere, and all my particles are on spherical trajectories, it will stay a sphere. But if I have these spiral arms, then I have a difference because, why will it stay a sphere? Because every point, this guy always sees the same potential in both directions. So he doesn't ever feel anything other than the same force in left and right, right? But when you have a spiral arm or a bar, then I'll have a star and he'll feel a little bit more force to one side than the other. So the spiral arms have extra mass, and so they can drag things in and out radially. So that's good for bulk radial migration. Like if this star is actually going to go in a lot, the spiral arms can do that. And they can torque you both directions in and out depending on where you are in the galaxy and with relation to the spiral arm. But outside of that, there's just random motions. So say I've got an elliptical galaxy. Let's forget about all of the structure. Elliptical galaxies are basically round. A galaxy going around this is going to have some random extra motion on it as well, and that's caused by the interactions of all the rest of the stars. So the potential isn't smooth in the galaxy. If it were smooth, then all the orbits would be nice and smooth, but it's not. It's spiky, and you can see that when you're traveling through the galaxy. Sometimes you'll be closer to another star and sometimes further away. That'll cause the paths to wander around and give you a randomness. The more randomness that you experience, the more time you've been there, the longer you've been in the galaxy experiencing all these random forces, the more random your velocity is going to be. Okay, you only have one velocity. Now here in this story, I'm pretending that you are a star. You only have one velocity, so what does that mean for it to be random? I mean, out of concert with the average velocity of the potential. So if I have a thin disk like this, I have a bunch of things in it, those things have been around a long time. They're going to have experienced lots of little motions that will send them in different directions. And the longer they've been around, the more their velocity vector is no longer like that, but then like that. So when the velocity vector is in the plane of the disk, you stay in the plane, but once it starts to get kicked out, then it can get kicked out more. And once it gets kicked out further, then it'll get kicked out further than that, because that process will just continue. I think that was somebody else's question. Why do older stars have higher peculiar velocities? That's what I just said, yeah.
What normally moves them around again, I'm sorry?
Gravity. It's the only force we have is gravity, and gravity comes from the collective potential. So, okay, ignoring basically everything else, here is galactic dynamics in 4 seconds. Let me put this up. Here's everything that you need to know, but not with any solutions. Oh, come on, wake up. I didn't test the camera was going to work, and now it's not working. Uh-oh. Can I edit the camera while the video is going? Well, let me do that. I don't know. That's irritating. I'm going to stop the recording. So this recording will be in 2 places. Sorry, I got to fix the camera. Now, okay, everything that you need to know about galactic dynamics. dV/dt is the acceleration. Is the gradient of the potential. This is the force from gravity, but calling it the gradient of the potential is way easier to deal with. So my velocity is dictated by my potential. We call this little g. I'll make that guy a function of position too, because this g isn't constant. This changes. So my velocity is given by my potential. My potential, del squared phi, equals 4 pi g rho. This is the mass density. So the potential comes from the mass density. This sentence is just a statement of Newtonian gravity. So this just says F equals gmm over r, with a little bit of calculus and some integrals in there, but it's a completely equivalent. If I integrate this twice and integrate this, and then you got to integrate by parts, and then you got to invoke this weird identity, then you'll see F equals gmm over r. So the velocity is given by gradients of the potential is given by the density, and the density is set by d rho dt is set by minus div rho v is set by the velocity again. So I have this triple of processes that are all tied to each other. I've got the velocity of the stars, which they're flying all over the place. Where they're going determines the density. Where the stars spend their time determines the density. The density determines the potential, and the potential determines the velocity again. So all of these just sort themselves out. I can rewrite this in a more general form called the Boltzmann equation, where instead I just write one equation that's got a bunch of terms in it, which is equivalent to these three equations. But these three equations describe everything that's going on. So when I talk about the potential, this is what it does. The potential gives me velocity, and it comes from the density. So that is the sum total of the physics of a galaxy. Now, actually solving this is very difficult, so there's textbooks and classes on that. The first astrophysics class I ever took was on galactic dynamics. It's a super interesting and heavy topic. Okay, so is our idea of dark matter as like the ether from a long time ago, or is it more than that? What was the ether? What was it for? What was the primary purpose of the ether back in the day?
Medium for the light to travel.
Right. It's a medium for light to travel through. So it's not there. What does light travel through?
Anything. Well, vacuum.
That doesn't make any sense. Photons doesn't care about the vacuum. Yeah. Yeah. At the end of the day, that is the answer. They just do. What do they do? Okay. How's a photon work? Oh, sorry. Wrong class. I can't derive it. We haven't done it there yet. Oh, maybe I'll do it real quick. So the time derivative of the electric field is space derivatives of, they'll write this down, it's not right, is space derivatives of the magnetic field. Okay, it's a curl and stuff, and there's a minus sign and a C. But I'm throwing all that out, I just want to get to the relationships. So time derivative of electric field is space derivative of magnetic field. Space derivative of magnetic field is, my hand likes to write that one better like that. Let's write curl of B, and this is minus 1 over C curl of B. So time derivative of electric field gives you spatial structure in the magnetic field, and the other way around. Time derivative of the magnetic field gives you spatial structure in the electric field, and the other way around. So when I have a photon, it makes a little magnetic field. In the process of making a little bit of magnetic field, that magnetic field has some structure, because you don't make it uniform in space everywhere. You make it in a point, and it's got some derivatives. So I make some magnetic field, it's got some structure, that gives me some electric field. That gives me some magnetic field, which gives me some electric field. So it's like you get some electric field, which makes a magnetic field, which makes some electric field, which makes a magnetic field. This is like the cartoons of Bugs Bunny when he was on the track, and he would pull out the track from behind him and lay the track down while the train is going forward. It's exactly like that. So that's how a photon works. So we just didn't need the ether, because the ether was a hole in our understanding. And the answer was so much weirder than what you would have come up with if you were out there looking for a medium that the photon comes in. What is the answer? The problem, what's the problem? The big problem is, if I have a gas like this, it supports sound waves. And if I start running really fast, I can run relative to those sound waves, right? So now if I'm in the vacuum of space and I start running really fast next to a photon, what do I see? doesn't make any sense. I can't Lorentz boost in empty space. There's nothing that I'm moving past. It's empty space, right? So the solution is everybody measures the speed of light the same no matter what you're doing or where you're going or how fast you're going. Every photon is always going c regardless of you. And that's a weird solution. That's the solution to what does light travel in. The answer to what does light travel in is light does whatever it wants. Everybody measures the same thing, and then things get really weird. So in a way, yes, it's similar. Like we've got this thing we don't understand. We've got a hole. The dark matter, though, is a little different because we see these measurements and we're like, well, okay, that thing isn't behaving the way we want. This thing isn't behaving the way we want. All of these things aren't behaving the way we want. There's a lot of data that is out there that supports, hey, there's something wrong. And so that's the basic thing that matters. So that's a super interesting comparison because they are both like really fundamental holes in our understanding. Like how does a photon move? That was a huge problem. It took people like Lorentz and Einstein to really come up with how that works. So the answer to what dark matter is might be something just as bizarre, like just as like, really, what the fuck? That's really, at this point, that's my bet, is that whatever the answer is gonna just break our brains because we'll get there. But I have this lecture. One of you asked, can we talk more about dark matter candidates? And I will. I got a whole hour and a half lecture on that that I'll talk about. But now that I've been given this lecture for a bunch of years and we keep not seeing the things that we were supposed to see 10 years ago, I don't know what's up. But there's a problem. So we'll talk more about the problem. Let's talk about the problem first. So anyway, I like this question a lot. I think it's a really, really thoughtful one. How much dark matter is there in our galaxy? It's about 10% normal matter. So when they say, in this calculation, 10 to the 8 times 10 to the 10 solar masses, how much of that is dark matter? That would be the next question. About 90% of it, 80 or 90% of it is dark matter. I will explain the work constants. Is there a local standard of rest for the universe? There kind of is. So there's this cosmic microwave background. And it's a bunch of photons that were released at the early universe. If you're traveling at a relativistic speed relative to that sea of photons, on one side of you, they're going to be redshifted, right? Or blue shifted because they're coming at them. And on the other side of you, they'll be blue shifted. So if you're moving and you make a measurement of the cosmic microwave background, you see a hot spot over there and a cold spot over there. So then you can say, okay, that's pretty straightforward to sort out. I'll just subtract off whatever that mean motion is, and I'm left with the normal motion. So that is kind of the local standard of rest, but it's a little bit more physically motivated in that it's a no redshift to the photons. It's make the C and B uniform. Whereas the local standard of rest that we'll talk about in a minute is kind of a fiction in the galaxy, and it's moving with the galaxy. So the local standard of rest is moving along with the galaxy. And it's a velocity space more than a physics space. More on that later. Would it be possible to view the universe from above? No, but also yes, because there's no center, right? So I am the center, so I am also the top. So it's impossible to view the galaxy from above because we can't get out of it because it's really far away. We would have to build a spaceship where hundreds of generations of people could live. It would be amazing. A whole community of people living for generations on a spaceship. I know I've seen too many space operas to know that would end in tragedy. Okay, so let's see. What would constitute an observation of a macho? So machos are viewed by lensing events. So they're too small to actually see. I'll talk about what a macho is for a second. I'm just going to answer the question now. I figure everybody read it, right? So everybody heard what a macho is. So there are these small, massive, so not massive like a brown dwarf. So maybe brown dwarfs could do it because brown dwarfs are really light and really dim. Black holes can do it. Black holes are really dim. So, but they're too small, too dim to see. But what you can see is when they go past a star, the lensing from the star makes that star get a little bit brighter. They're far enough away that they're not. If the object is right in front of the star, it makes the star dimmer. If it's far away, then it makes the star brighter because of general relativity. And we've done some surveys for that, and we've seen some. There exist machos, just not enough. And a macho was developed as an answer to a WIMP, which is one of my favorite things. Machos were developed by Kim Greist, and Joel Premack, his advisor, invented the WIMP. Seems like neither of them really exist. Let's see. So yes, they are theoretically detectable. We have detected some. There just aren't enough. How does the book come up with? Yeah, I will go through the geometry. Maybe not as satisfying as you want, but I'll go through it. How does the book come up with the velocity dispersion of stars? So this is an interesting question. So how do you measure where you are if you can't see the ground? You got to measure everything around you and assume that something is doing something right. So I look up in the sky and I have all these stars. Now, I know that we're all moving in the plane of the galaxy, so we're all going in this direction, so I'm going to keep that in the back of my head. I'm going to measure the velocity to each one of these stars, and I'm going to plot it. And I'm going to plot it, it's all relative to me, right? Because that's the only thing I can do. I can't do something relative to a fixed point in the galaxy because I can't get to a fixed point in the galaxy. So I'm going to measure all of these stars, and I'm going to get some, I get some radial velocity and I get some tangential velocity. And I'm going to measure a cloud of points. Now I know that that cloud of points is, once I take off the galactic rotation, not moving, statistically. Spinning around in a disk, but that I can take out, and then everything else is basically staying put. I'm basically staying put, everything else is basically staying put. So if this cloud of points is on average not moving relative to the galaxy, but I measure some center. I have some, so this is the radial velocity and this is the tangential velocity, should be there. I measure a collection, I'm at the center of that. Not moving is at the center of that. Does that make sense? So the average of this cloud is what not moving is. So I measure everything and I can get what the average is, and then I measure myself relative to that, and then I can sort out what my velocity is. Does that make sense? I should make a homework problem on this because I think that would be more useful. Because I think putting your hands on it would be real valuable. Also, I've got another story that I'll talk about that again in a second. Why are the components U, V, and W? Because it's shorter than Vx, Vy, and Vz, I think. But that's not uncommon. Why is the angular velocity of the galaxy constant? With radius, because of dark matter. Because what I want is for it to fall off like R. But it's not, it's flat. That's because the mass, there's a buttload of stuff out there. And that buttload of stuff keeps that mass doing doing the flat rotation curve story. I like this question as well a lot. Do the assumptions, such as pretending the orbit is circular, fit well with our understanding of the universe, even though we know that it's not circular? So this is a great question because I'm going to go through and make a whole bunch of really dirty approximations and wave my hands and say a bunch of stuff that's not actually true, but is true enough that we get enough of the story. So that's really a big part of the process of being a physicist, is getting things that are true enough to answer your question. If you're a mathematician, then you want things to be actually true. And if you're an economist, you just want to make money off the system. For a scientist, for a physicist, you're trying to come up with something that's approximately true based on your understanding. So it's all about making models that look mostly like what the universe looks like, but are simple enough for me to understand. So the way the process works is you start off with a thing that you don't understand. You make the dumbest model you can, which is usually super wrong, and you see how wrong it is. And if it's right, then hey, you understand the system. If I say I've got an atom in a well, I can treat it like a simple harmonic oscillator. And if the answer I get out is a simple harmonic oscillator, then I was close enough, even though the potential isn't actually going to be perfectly quadratic or whatever. As long as the answer is close enough to the science, then you can declare some kind of victory. But if you don't get the right answer, then that model was wrong. So kind of, I would sum up the whole of this class, and really the rest of your science is studies, is this balance of making assumptions that fit what the universe is doing. Now there's some basic ground truths like conservation of energy that we'll say are true always, and then I'm going to tell you later that conservation of energy is not true either. Yeah, one of the saddest conversations that I have to have, and I have to have it periodically, is so we have these redshifted photons, right? Photon gets bigger, energy goes down. Where's that energy go? Nowhere. It's just gone. That sucks. I hate that. But general relativity doesn't require energy to be conserved. So that energy can go somewhere else. Now people will tell you that it powers the expansion, but that's not true, because it's a gradient that powers the expansion. Anyway, so I like this question. It caused me to go on a rambly tangent. Assumptions and approximations are really the game, and it's always about making an assumption and then see how wrong you are, and making a better assumption and seeing how wrong you are. Omega of r is the rotation curve. Omega of r is the rotation rate in the angular velocity versus position, which is the thing that we want for these things. And I'll come back to that in a second. R naught. Let's see. LSR and R naught. LSR and R naught are actually vastly different, because the local standard of rest is about velocity, and R naught is about spatial position. So local standard of rest is my velocity relative to the galaxy. It's actually relative to the galaxy, but I'm not moving. So it's relative to where I am in the galaxy. R naught is relative to where I am in the galaxy, and LSR is relative to how fast I'm moving in the galaxy. Let's see, do all galaxies have dark matter? Probably. There are a couple really little fuckers that maybe don't, but maybe they only have like 8 stars, so I don't trust those measurements. So there's a whole population. People are going out and looking for these little dwarf galaxies that don't have any dark matter in them, and they're finding them. The measurements are dodgy, but they're interesting enough that everybody's talking about them. So probably, maybe there are some that don't have dark matter. But it's not just spirals. Big ellipticals have dark matter too, and we'll talk about that, and you can see it. And how is it shaped in the universe? It's distributed kind of like the galaxies are, but it's bigger than the galaxies. So, I really should have. I don't have any internet, so I can't pull that up. When we get there, I'll pull up some structure formation videos. The dark matter is distributed in the universe in like this spiderwebby pattern with, and where the spider webs intersect, there are knots of galaxy clusters. So it's kind of spread out everywhere. It's not uniformly distributed. It's clumpy. It kind of looks like neurons. Kind of looks like a brain if you look at a neuron dendrogram. Dark matter candidates. I will talk about dark matter candidates later. Basically, there's 2 flavors that we care about as astronomers. Either there's the math is wrong, there's an astrophysical object like a black hole or a brown dwarf, or there's a particle like a WIMP or an axion. So one of those. Let's see. Do Kepler's laws only apply to solar systems? This is a good question. When does Kepler's law apply? When does what apply? So the equations that I wrote down that I have now erased, those are always true. Those are basic fundamental constituent equations. If I have something like if I have something like a galaxy, so what Kepler's law says is basically this. So let's answer this question this way. What Kepler's law says is basically this: v squared equals gm over r. So whenever I've got a sufficiently relaxed system, then this is going to be basically true, and everything else falls from that. So everything else comes from the central force properties. So Kepler's law, they're an approximation that says all my mass is at the center, and I'm orbiting it. But it's a pretty good approximation for basically everything that we do. If I want to talk about how a galaxy forms, Kepler's laws are insufficient because they don't get the rest of the dynamics. Oh, yeah, so the spike in that curve, let's see, do I have it up? Pardon me. Because I think actually it's not in my... this, where we at? I appreciate this question because you correctly interpreted what was going on. Where has it gone? I think it's in the slides. I'll come back to it. So there's this velocity diagram of carbon monoxide radiation. And there's this huge spike in the middle from the central molecular zone, which is the part of the bulge. So there's a lot of molecular gas there. Why there's so much gas there and why it's forming stars so aggressively is not really obvious. And then there are some blobs that are super dense and not forming stars, and that's weird too. But there's a lot of molecular gas in the bulge because there's a lot of stellar activity. There's a lot of stars that blow up. Dead stars make dust. Dust makes CO. Why is there a dip in the velocity at 3 kiloparsecs? It's just at the edge of the bulge. So things are rotating real fast close to the bulge. Then we have this disk, and the disk doesn't have as much stuff. So as you get away from the bulge, you see that. Ask that question again when I pull that up. This was a challenging section. Yes, it was a lot of math. Work constants, I'll explain what the work constants are in a second, and I think that I said everything else. Anybody have any other questions about any of those things? So I'm going to give, how am I doing? How am I doing on battery? Whoa, 56. Yeah, I'm just going to plug in, thank you. That's not going to last much longer. So, we have all these disks. And the scale height, where'd my scale height go? The scale height goes like temperature over gravity. So when the temperature is high, the scale height is high. And temperature, remember what we said, temperature is energy per particle, so I can talk about the temperature of the stars. That's just the velocity of the stars per star. So if the velocity of the stars is higher, then I'll have a thicker scale height. And the velocity of stars gets higher when they're older and they're randomized more, so they get more of these random encounters. And so the old stars see more kicks, yeah. Okay, no worries. Okay, there are a bunch of tables in the book. Please consume the tables. Read what's in them and read the numbers and get familiar with what the numbers are. So for the Milky Way, so here's a good one. For the Milky Way, this describes what the neutral gas disk is doing, the thin disk, the thick disk, the bulge, the stellar halo, and the dark matter halo. And it talks about the mass of each one of those. So the dark matter halo is about 55 times 10 to this 10. Yeah.
So I have a question about the galactic halo. Is there is dark matter just inside the halo, or is there also some outside the halo as well?
So that if I look at so the galaxy looks like that. There's dark matter here. There's probably some dark matter out here too. If I have another galaxy over here, it'll have a ball of dark matter. Maybe these guys are touching. I don't know. Maybe I got another denser ball of dark matter in here. So the dark matter is kind of clumpy and everywhere. Doesn't really go to zero anywhere. Whereas the bulge is only 10 to the 10 solar masses, and this is the dynamical mass. Yeah.
What is the little blob up on that?
At the top,
Yeah.
that's a high velocity cloud.
Okay.
I'll talk about those in a second. Yeah, let's just race on towards those things. I did this. See, I think I covered everything here. So the total density is given by several exponentials. So there's the mean density. There's an exponential for the thin disk. There's an exponential for the thick disk. Notice it's less dense than the thin disk. It's thicker too. And then there's an exponential for the radial component that goes outwards, and it's got a radial scale height. So if you want to describe the total density of the disk, it's these couple of exponentials. So that's the whole distribution of what a spiral galaxy looks like. Okay. See, anything else? What else do I want to say about disks? I think that's it. Okay, the bulge looks like an elliptical galaxy. I'm going to talk in detail about elliptical galaxies in a day or two, and we'll go over it. I'm not going to go through this Dvock-Allures profile today because I don't have the time. I'll go through it more in detail. I'll give you the nickel tour. Basically, when I look at the brightness profile as a function of radius, I get this curve. It's called the Dvock-Allures curve. I can't spell it. There's a lot of use. Dvock-Allures. Oh, it's right up there. And it looks like kind of like a power law. And if you do some math that I'm going to skip, you see that it also looks like a virialized sphere. So if I take a virialized sphere, and this goes like rho, the density goes like 1 over r squared. Kind of. I'm going to put this in quotes because it's not exactly 1 over r squared, but it's kind of like 1 over r squared. 1 over r squared is the major behavior. This blows up at 0, so we got to do something at 0. But 1 over r squared is the basic process. If I take a virialized sphere like that and I make it emit light and then I project it onto a surface, and I look at the brightness profile of this, then I get the Dvock-Allures curve. The upshot is Dvock-Allures means virialized sphere. So it looks like a relaxed object. About 10 to the 10 solar masses. The profile goes kind of like 1 over r cubed. Contains both old and young stars. So it is old and has young stuff in it. So there is star formation going on currently. But the object itself is very old. It probably is much older than the galaxy, though it was formed kind of coeval, so it's hard to say, what really is older. But it's round and it's a big blob in the middle. So it's like this one. There's a big blob in the middle of this galaxy where things kind of change a little bit. So then we talk about the halo. I'm going to talk about the halo really fast. Now questions took me a minute. So there are these globular clusters we've talked about. They're useful because they're rattling around the galaxy, so you can measure what the galaxy looks like with them. And they're old as hell, so you can measure the age of the universe with them. That was one of the first problems with developing a complete model of the universe, is because the simplest things that you can do about the expanding universe tell you that there are stars that are older than the universe. So clearly the simplest model is not right. The second simplest model works out pretty well, though, so we'll get to that. So there are all of these halo stars up here. and they're all metal poor. Why do I care about metal poor? That means that that star wasn't born in a dirty nursery. So the metal content of a star comes from where it was born. So if I have a star with a high metal content, it was born from clouds that had high metal content, which means those clouds experienced a lot of supernova. So that means that star was born more recently because it has formed out of stuff that took a long time to form. If I have a metal poor star, that was formed in a relatively pristine environment a long time ago. So we have all of these stars in the halo that have very little metals, so we think that the oldest stars in the universe are going to be up there. So there are many star surveys that are looking at these, at all these stars, trying to find some really old ones. Remember that 0.8 solar masses? We can find a 0.8 solar mass that has no metal lines, then we know we found a star that was formed basically at the beginning of the universe. Nothing's been found, but they have found some very old ones. There are also all these. This is a map of high velocity clouds. There are these big clouds of hydrogen in the galaxy that are kind of up and floating around the galaxy. There's a lot of crap in the halo of the galaxy. There's a lot of gas up there. There's about as much gas in the halo as there is in the disk, but it's really spread out and it's really hot. But there are some blobs of it that are cold and dense that you can see. It's not really clear why these objects are cold and dense. It's probable that they're wrapped up with magnetic fields, and the magnetic fields keep them confined. But I've only seen one measurement of that, because it's really hard to measure if magnetic fields are holding these blobs together. Okay. Oh, the ISM. I forgot I had to talk about the ISM. Sorry, collecting my thoughts. All right, so the interstellar medium is the stuff in the galaxy that's between all the stars and isn't the dark matter, but is everything else. And it comes in phases that are roughly in pressure balance with each other. So you have, P equals rho T. That's the ideal gas law with all of the units set to 1. So pressure is density times temperature. So density goes down, temperature goes up. You can be in balance with something that has, so high temperature, low density is in pressure balance with low temperature, high density. Does that make sense? So I have cold stuff that's dense, hot stuff that's not dense, they can be buddies. It's weakly pressure, it's not perfect pressure balance everywhere. There's lots of pressure gradients driving massive flows, and there's lots of violence in the interstellar medium. But for the most part, you can treat it as a multi-component fluid with a bunch of different phases in it. So the bulk of the mass is in molecular clouds. And so these are cold, like 10 Kelvin. 10 Kelvin's really cold. And they have densities of like 100. And there's a lot of it. And you can't see through a lot of it. And it's where stars come from. So all the stars form in molecular clouds. I don't know if that's actually a true statement, because I think that stars can form not in molecular clouds, but they don't usually. Less dense and higher temperature. The cold neutral medium is like 100 Kelvin, and it's a little bit less dense. There's not as much of it. The warm neutral medium is then 6 to 100,000 Kelvin. This is the stuff that's neutral but near these warm ionized regions, which are 8,000 Kelvin. This isn't a range, this is 8,000 Kelvin, because that's where ionized hydrogen can cool to. Ionized hydrogen can cool like crazy because it emits photons. It emits photons until it all recombines at 8,000 Kelvin, and then it stops cooling. So there's this whole population of 8,000 degree gas. H2 regions are dense ionized regions that are near young stars. And then we have all this coronal gas, this circumgalactic medium, which is millions to 10 million Kelvin. Gas that's this hot doesn't really reside within the galaxy very much. It usually leaves. Yeah.
Why is there nothing that's like between 100 and 6,000 degrees Kelvin? Like, why? Why is there just a big gap?
That's a good question. So these are all kind of approximate. So there's plenty of stuff that's in, like if you pick a temperature, you'll find some gas that's there. But for the most part, there's kind of underlying physical processes. So if you can get, so if you're at 20,000 Kelvin, you can cool to 8 pretty easily. Then if you can find another medium that can cool you more, then you're not going to stick around at 7,000 Kelvin. You'll just keep cooling. So it's really because there's this bump at 8 where stuff likes to sit, and then stuff at 10 where it can really cool pretty radio. Everything else in the middle is really not in equilibrium. It's changing. It's going from one form to another. Yeah.
This might be maybe an honest question, but how come the air so hot up there? Is it right next to a star or something?
Yeah, it's filled with stars. It's all full of stars, and it's not very thin, or it's not very thick. So you have light years of gas and UV photons coming off of massive stars that just fill the galaxy. And those UV photons excite everything. They ionize all the hydrogen, and they do all the heating. That's a great question. I'm not going to say a ton about the ISM because I don't actually need the ISM for most of what we're going to talk about, but I like the ISM personally, so we'll talk about it some. So these are two pictures that really, that's where this TV doesn't do a good job. You should download the slides and look at them. This is H alpha in various different regions of the galaxy from this survey, the Galpha H1 survey, where they measured neutral hydrogen throughout the whole galaxy. And they find that it's in these fluffy kind of spiderwebby like patterns. And the different colors here are different velocities of gas. So they take a picture of the gas in the radio, and a radio gives you velocity information too. Radio telescopes are really cool. So you get velocity information about what this gas is doing. And this gas is moving at 40 kilometers a second. 40 kilometers a second. How far away is 40 kilometers? Thomasville is like 40 kilometers away, right? So this is really fast gas. So this is what the neutral gas looks like. These pink things are what the H2 regions look like. So H2 regions are kind of compact bubbles. And it's pink. I know that that's an H2 region because I know what that color is. That's H alpha. They recombine down through H alpha. As they're recombining, they give you H alpha as they're combining down to a neutral atom. But you get all that H alpha when you have a lot of recombination. And then you have dust, like these dark lanes. This is dust. There's molecular gas. You guys have probably all seen this. This is one of my favorite things.
Yo, look at my wallpaper.
Hey, don't. I love this because this shows you why we need JWST. You see how much crap you can see inside of this cloud? The image on the right is JWST, and the image on the left is Hubble. Hubble is also a super important telescope, so I don't mean to talk smack about Hubble. It just can only see in the visual. If you go to the infrared, then you can see stuff like this red thing. Here is a baby star. You can't really see it in here, but it's what's holding on right here. This red guy right here. There's a little star right here. You can't really see in the other picture. There's a dude here. It's kind of magnificent. And you can see through it. Like, you can't look at this. You can't see any of this because there's this hazy crap in the way, but you can see right through it. You can see all these stars. Anyway, I like JWST. I'm pretty stoked about what it's going to tell us. This is what the magnetic fields look like in the Milky Way. So this is a measurement from dust polarization. And yeah, so I got like 15 minutes left. Yeah, I'll do this part. I don't really need to talk about how you measure magnetic fields, but I think that all y'all would find it interesting, so I will go through that. Also, I like it. I think it's really cool because it's really tricky to measure. So let's talk about. Come back. Let's talk about the non-thermal components of the galaxy, and these are cosmic rays, magnetic fields, and gamma rays. What do I mean by non-thermal? That means things that aren't made by thermodynamical processes. There's other processes that make these things. Cosmic rays and gamma rays come from ultraviolet explosions, and magnetic fields come from the dynamo, and I'll talk about each one of these a little bit. But let's talk about the magnetic fields. So the galaxy has this magnetic field that's about 6 microgauss. How big is a gauss? Is that?
Pretty big.
How big is a fridge magnet? What's the magnetic field strength of a fridge magnet? That's the one magnet that I know everybody's probably put their hands on, right? A fridge magnet is about a half a gauss. How many gauss are in a Tesla?
10 to the 85. 10 to the -85 Gauss lambda.
Yeah. It's 100,000 gauss in a Tesla. So the mag lab makes fields that are like 40 Tesla. So that's like 4 million times larger than a gauss. And this is a microgauss, so this is like 12 orders of magnitude larger in the mag lab than what you have in the vacuum of space. However, we have 100 kiloparsecs of this magnetic field. So there's way more magnetic energy, all told. But it's very thin. But it's important, and it's there, and it's in the way, and it's doing stuff. So how do we measure it? I'm going to spend the next couple of minutes talking about how we actually measure the existence of a magnetic field in the galaxy. And this thing here is just one of my favorite images ever, because this is an image of what the magnetic field looks like over the entire galaxy. Planck measured this. And it measured it using polarization. So, okay, so I'm going to talk about polarization. I'll talk about Zeeman splitting, I'll talk about synchrotron emission, and I'll talk about Faraday rotation. And I'm going to give them all kind of a quick drive-by, but that way you guys have seen how we know. Like, I'm going to tell you there's a huge magnetic field. You shouldn't believe anything that I say, because I make stuff up all the time. Okay, so when I have a magnetic field and I have dust, what's a dust? So a dust, remember I showed you that picture, is this kind of candy bar looking thing of blobs. It kind of looks like a payday bar with little nodules on it, or other things that are long and blobby. It's kind of elongated, and they're big objects, and they're just made out of carbon and metal, like iron and magnesium and stuff. So they got a lot of loose electrons. So we got all these UV photons in the galaxy. So when I have a dust grain, which is made out of a bunch of carbon and magnesium, has all these extra electrons, not extra electrons, just loosely bound electrons. Those electrons are really easy to kick off with UV photons. So I hit my dust grain with a UV photon, and the photoelectric effect kicks off a photon, or an electron. And then that electron races around the interstellar medium and heats it up a little bit, and then I have a charged grain. So now I've got a grain that's got charge on it, and it's going to know about this magnetic field. It's going to rotate, because things move. It's going to rotate, and it's going to line itself up so that the grain is perpendicular to the magnetic field. Why perpendicular? Because as it's spinning, it's going to make a little magnetic moment, and those guys are going to line up. Magnetic moments will line up. So then my dust is all lined up. When my dust is all lined up, it makes a polarized signal. Not a very strong polarized signal, but it makes a polarized signal. So this is good for measuring the direction of the magnetic field, unless you want the actual direction of the magnetic field, in which case you're off by a factor of 2. Because the way I drew this dust grain here, so this ultra simplified schematic, the lines are magnetic fields, and this thing is a dust grain. This guy's rotating, and it's going to emit light that's going to be polarized perpendicular or parallel to its axis. So the electric field is going to come out along this direction, because the electrons can go along that direction, and so they will vibrate in that direction, so they will make photons that are polarized in that direction. Have you guys come fully to grips with why polarized sunglasses work and why they're great? So when you have a surface has electrons in it. If I have a photon that hits it, those electrons move and give off their own photons. That's why things reflect. Things don't reflect because the photon bounces off. Things reflect because the photon excites this electron, and that electron makes its own photon, which then leaves. Does that make sense? That's how reflection works. Now, when I'm looking at this photon, it can go in this direction, or it can go in this direction, out of the page. If I'm over here, and I'm looking at this photon, I'm only going to see the photons that are going this way because the photons that are going this way are squashed by geometry. So I only really see these photons. So if I put on a polarizer that's this way, I block the reflection off the surface. Emission is similar. I've got a dust grain and my electrons can only move along the dust grain. I mean, they can move side to side along the dust grain too, but the wave function is big compared to the grain side to side, so it can only move along the dust grain. So it makes an electric field that's polarized along that dust grain. So I take a polarized map of the sky, and one thing that I'm missing here is which direction the magnetic field is going, because it doesn't matter. I switch the magnetic field, this thing's going around, it doesn't care if it's going around and that thing's pointing that way or that thing's pointing that way, it's just going to go around. I can switch the direction of the magnetic field and it doesn't matter. So polarization tells you kind of the direction of the magnetic field, and if you're really wishful in your thinking, it will give you the strength of the magnetic field too, but I'm not even going to bring that up because it's dodgy. It doesn't do a very good job of measuring the actual strength. Well, okay, that's a lie. It does a fine job. But it's not very accurate. So it's good for the direction, but not for the magnitude. Zeeman splitting is the other mechanism we're going to talk about, and this is this level splitting that I mentioned the other day. So here I've got an atom with two states, two electron states. I've got the 2p and the 1s orbital. So this is hydrogen in the ground state. Hydrogen doesn't do it. You need something bigger. So this is like the rho vibrational modes of CN, some other atoms and some other molecules. Anything with a big magnetic moment in the nucleus. Magnetic moment with one proton is pretty small, but carbon is pretty big, and carbon CN, which is cyanide, which just happens to be in outer space, is a big polar molecule. So it does this a lot. So I've got any kind of transition from one state to another. The magnetic field makes that lifts the degeneracy so that the two states are different, because now we have this magnetic dipole in the center and a magnetic field outside, so the magnetic dipole of the electron is going to matter. So that splits the energy. So the magnetic field splits the differences in the energy of this upper state, because now it cares where the electron is pointing. Now I can tell the difference if I transition from this state to the ground state versus this state to the ground state, because the two energy levels are different. So how do I actually do that measurement? Turns out it's actually a real headache. That is really noisy, but it works. So that's pretty sweet. So you get, draw pictures. So if I have some spectrum, it's going to look like that. There's going to be some rest wavelength, and say this is 1500 gigahertz or something. Okay, that's a wavelength, and this is a frequency. Those two are interchangeable in my head. So, see that. So this is whatever my rest wavelength is, and the width of this spectrum. So this is what I measure with my telescope. So I've got all of these velocity channels. Say this is a radio telescope. I like radio telescopes. Radio telescope lets you measure a bunch of different wavelengths at once, so it lets you measure a bunch of different velocities at once. So this is what I would observe if I'm looking at an object that has some temperature. The width of this spectrum is set by the Doppler shift from the thermodynamics from the thing having a temperature. So the whole cloud has some net motion towards me. Some of those molecules are moving net away from me. Some of them are moving net towards me. The ones that are moving away from me will be a little longer. The ones towards me a little shorter. So it's broad. This is what I measure when I measure basically anything. It's always some width. Now, this Doppler shift, or this Zeeman splitting shift, shifts how this spectrum is going to be from the two states. And we get something that looks like this. So my upper state looks like this. My lower state looks like this. Ta-da! You can't really tell the difference between the purple and the blue points, can you? Because the shift is really a lot smaller than the noise in the system. That's a problem. Nature was nice, though, because these two photons are oppositely polarized. One of them is left-handed polarized, and the other one is right-handed polarized. Now I have a win. Man, I'm sorry. Just realized Squirrel Brain is just reminding me that I said something totally wrong to a student the other day about circular polarization. Anyway, so I have these two signals that are basically the same. They're shifted a little bit. If you really look, you can see that the purple curve is to the left of the blue curve. But if you have a measurement that's also noisy, just by looking at the spectrum, you can't see them, but you can take two polarized spectra, and these two, the blue and the purple, have opposite polarization. So I take the difference of the blue and the purple, and I'm left with this. And this S-shaped curve, from the height of how much it shifts. So if they're on top of each other, the shift is 0, and as they get further away, the shift actually grows. From the shape of this curve, you can sort out what the magnetic field strength is. You can sort out what the difference between the two states is, and you can sort out what the magnetic field strength is. Does that make sense? No? Back up and do it again? I'll back up and do it again. So, this is the spectrum if there were no magnetic field. Right? Now, if I add a magnetic field, then that splits the levels into two different states, and I get an upper state and a lower state. So when the electron goes from the upper state to the ground state, I'll get a slightly higher energy photon than if it goes from the slightly lower state to the ground state. So I get two populations of photons that have a little bit different, that are a little bit different in energy. Not a ton, but the higher energy ones are all spinning to the left, and the lower energy ones are all spinning to the right. So I take an image with a left-handed circle of the polarizer, and an image with a right-handed circle of polarizer, and I take the difference. And the difference tells me how much shift I've got. That tells me how many photons that I have on the left versus how many photons that I have on the right. Does that make sense? I can't just take a curve that looks like this and a curve that looks like this, because the noise isn't there. I can't say, well, this one peaks somewhere here because it's noisy as hell. But with the polarization, I can see where the difference is. Okay. Synchrotron emission. If I have a bare magnetic field, and I should say this is almost every method that we have for measuring magnetic fields. There's one that I didn't put up here because I didn't think that it was possible to measure, but people have started doing it. That's pretty cool. So there's another one called the Golroy-Keel-Office effect, but I'm not going to talk about it. Everything else is hard enough. So synchrotron radiation is important for a lot of reasons. So synchrotron radiation is how they make X-rays, X-ray sources. So if I've got a magnetic field, an electron, because F equals QV cross B, electrons go on circles. And because they go in circles, they're lined up to be basically perpendicular to the magnetic field. That's pretty dope. And when a charge moves, when a charge changes direction, anytime a charge accelerates in any kind of way, every acceleration of every charge gives you radiation. When you wiggle an electron, it makes a radiation. And when you wiggle an electron in one direction, it gives you polarized radiation. So synchrotron radiation, this is typically in the infrared, in astrophysics, but you can make electrons do ridiculously high energy things. So you can have synchrotron radiation in all kinds of sources. So there are a couple of machines in the United States that are synchrotron light sources. But in outer space, we see this synchrotron radiation. Typically, we see this in the high latitudes of the galaxy, wherever you have relativistic electrons. So if the electrons aren't very high energy, then this spiral is really tight and you can't see it. So you need the electrons to be relativistic to spiral around, but then you can get emission. And the gyro radius is mv. V is just the energy of the electron over B. M and Q you could just measure. That's the mass and the charge of the electron. You could just measure those. So what you're left with is the energy of the electron and the magnetic field strength. So if you know the energy of the electron, then you can back out the magnetic field strength, but that's kind of a big ask. So synchrotron emission is another way that we measure magnetic fields in the galaxy, in the universe. So we can see synchrotron emission on enormous scales. Polarization we only kind of see in the galaxy. Zeeman we only see in really little objects. Yeah.
So that radius is the radius of like all the time.
Yeah. This is the gyro radius, and it's mv over qb. And you can sort out what this circle is. It's really not very hard. If you take this and write it down like a pair of two differential equations, this is dx dt and this is x cross b. It's two differential equations. You couple them, you can sort out. It turns into a circle because I get y dot equals x and x dot equals y. That turns into a circle, and you can sort out what the radius of the circle is. It's not super challenging, but I'm not going to do it right now. Where am I at? Last thing. The last thing is Faraday rotation, again with the polarization. Magnetic fields are basically all about polarization. Every single one of these that I've mentioned is all polarized, and polarization is super important for us seeing the magnetic fields. And here is no different. So if I have a magnetic field and I have a population of electrons and I have a radio wave that comes through like this. Okay, I'm going to stand here and look down that way. If my radio wave is like this is the electric field for my radio wave, is oscillating up and down like that. I got these electrons. I got a magnetic field. It's coming out of the board. What's the electrons do? Well, the electric field, let's say for a second the electric field is accelerating the electrons in that direction. What does this electron do? Yeah, it'll go like this. And then it's going to come back down and go like this. So when it goes down, it goes the other way. So the electric field pushes it up, the magnetic field pushes it to the right, so you get something that looks like this. And then it comes back down this way, so it rotates the polarization vector. So my polarization vector comes in like this, but then I got all these electrons that are going like this, so my polarization vector of my resulting photon rotates. And that rotation, here's how it works. Here's how we can do anything. That rotation is dependent on the electric field, or on the wavelength of the photon. Longer wavelength photon is going to accelerate something a lot more, so it's going to bend it more. So it's going to rotate the photon more. So I can take my radio telescope and take a picture of a polarized source, like a quasar, and then I plot the polarization angle versus wavelength. Remember, radio telescopes let you measure a bunch of wavelengths at once. So I measure the angle versus wavelength, and I plot it. And I get a line. Actually, I plot it against wavelength squared, and I get a line. And then that wavelength is this number called the rotation measure times lambda squared. And the rotation measure, that is a lot of crap to go through to get a magnetic field strength, right? The rotation measure, this is where the magnetic field strength is the integral of the parallel magnetic field times the electron density along the line of sight. So it's equal to the parallel magnetic field times the average electrons times the length of the cloud. So I get this line, and I measure the slope of the line to get the magnetic field. This is called Faraday rotation. And now I'm over time, so now I'm going to stop talking. But those are the ways that I know of to measure magnetic fields in the galaxy.